Before we proceed further, let's take a quick recap of scientific notation, because the linear regression output has a lot of scientific notation typically. So let's understand what's going on, right? So for example, suppose you see a number like minus 1.08 e minus 0.1, right? So when it says e, right, that stands for 10 raised to a certain power. So e minus 0.1 basically says 10 raised to the negative 1 power, which is basically divided by 10, right? So negative 1 power is when it goes below in the denominator. Okay, so this is basically this number divided by 10. So that's going to be minus 1.08 divided by 10, or minus 0.108. Okay, whereas if you have e minus 2, that means divided by 100, that is raised to 10 power minus 2, which is the equivalent of dividing by 100. So therefore this number would be 3.286 divided by 100. Positive powers obviously raise 10 to the appropriate power. So minus 1.777 e plus 0.1 is minus 1.77 10 raised to 1, which is 10. So e plus 3 would be e plus 0.3, or e plus 3 would be multiplied by 1000. And e plus 0.0 is of course multiplied by 1, right? Because 10 raised to 0 is 1. So this is how you interpret scientific notation numbers in linear regression output, or any other time you see it in R. Okay, so the key point is, let's say again we revisit our old linear regression output for the Boston housing data, and basically we looked at how to interpret these significance codes. Okay, in other words, if you have at least one star, then it's significant. Another way to look at it is to look at the estimate plus minus 1.96 times standard error. And that interval, plus minus, of course, it's going to define an interval for you. Minus will give the lower limit, plus will give the upper limit. So this is defining an interval. And if that interval contains 0, then you cannot rule out the possibility that this coefficient is actually 0 and we are seeing a value only because of a crazy sample. Okay, so if that interval contains 0, that means the coefficient is not significant. So that's another way to interpret these stars. I mean, if you want to calculate it by hand, you can do that. So for example, here 2 stars, that means it's significant, which means what? Which means that this interval for this particular coefficient, if we calculate this interval, we should see that the interval does not contain 0, right? So if you calculate this using scientific notation, this is minus 0.108 and this is 0.03286, and if you did this minus 1.96 times this and plus 1.96 times this, then you will get this interval. The lower limit will be minus 0.14, upper limit is minus 0.075. Okay, so this interval is entirely below 0. It does not contain 0, therefore it is significant, and it's not surprising that you do see 2 stars here. Okay, so let's take an example of something that the regression output is telling us is not significant and calculate the interval for that. So for example, let's take Indus. Right, clearly it's telling us that this is not significant because there is no notation, not even a dot here. Right, of course, even a dot would not make it significant. We need at least a star. So if we perform the same computations for this coefficient Indus, then you see that the lower limit is minus 0.041, the upper limit is plus 0.082, and this interval contains the number 0, right, because it's going from minus to plus. Obviously in between somewhere is 0, and therefore this coefficient is not significant. No wonder you didn't see anything here. Okay, so if you look at the computation for root mean squared error, and we had this earlier, this is how you compute the root mean squared error. What you're seeing here really is yi minus y hat, and we are squaring that, and yi minus y hat is nothing but actual value minus predicted value, which is the very definition of residual, right? So the root mean squared error, you can look at the formula like this as well, sigma I equal to 1 to n residual I squared. That is, we take each residual, square it, and take the mean of that and take the square root of that. Okay, and of course, since we already know that the mean of the residual is always 0, this is really something like the standard deviation of the residual. Okay, this is almost the same as the standard deviation of the residual, which is almost the same as the residual standard error. And this is the reason we treat this residual standard error as representing our RMS error, right? So when we see linear regression output, we can take this particular number and treat it as the RMS error on the training partition, on whatever data was used to build the model. For that, the RMS error is directly given by this. We don't have to actually compute it at all. So let's look at these. These just compute the standard deviation of the residuals. It comes out as 4.683. And if you look at the residual standard error, it's 4.745. It's very close. Okay, so we don't really need to worry about this. We can just use this as the RMS error. So R squared, as we already know, this number, multiple R squared, is nothing but the coefficient of determination, or R squared, as we had seen earlier. SSR divided by TSS, that's what this number is. And basically on this particular output, it's telling us that the regression is able to explain 74% of the variation in the target attribute. That's what this is telling us, right? That's quite a high number. Regression is explaining 74% of the variation. So that's telling us that your regression is actually quite significant. That the regression is saying that all of these things are related to the price, and in fact that seems to be quite valid. Now you're seeing another number called adjusted R squared right here. We'll come to that later. We won't discuss it at this point. So finally, you see that there is a p-value at the end of the a regression output. This is basically saying that the probability, in reality, only the naive model holds, and that this regression is spurious, and it's just a fact of a crazy sample. Okay, so what this is telling us is that that probability is extremely low. It's almost zero. Okay, so once again, the R square, the coefficient significances, overall significance of the regression, all of them give us some confidence in the fact that our regression is really valid. All that said, since we are looking at regression solely from the viewpoint of predictive analytics, right, we are not trying to use regression in order to prove any underlying theory. We are just saying, look, I want to use this to make predictions. So because of that, we will mostly be concerned about the RMS error, right? So we'll run a regression, we'll see the RMS error and see, well, does this RMS error make sense in our context? If so, we'll go ahead and use the regression.